Welcome to this 3-minute summary of our paper, Core-Guided Model Reformulation. In this paper, we wanted to address one of the main limitations of constraint programming-based optimization, which is that while many constraint programming models have additive objective functions, CP solvers tend to underperform when trying to prove optimality on these problems. This is because the lower bound on the objective variable is often hard to improve. As an example, we have this simple constraint program here, where a CP solver cannot, without performing some search, find a good bound for the objective variable z. One way we could help CP solvers is to introduce new variables that combine objective terms and provide better bounds for these combinations. And this particular reformulation allows a CP solver to infer that the lower bound on z should be 4. There are, of course, many different reformulations possible, and some are going to be better than others. So in this paper, we wanted to find useful reformulations and try to apply them at the level of a high-level constraint programming model. One approach that does something similar to this is core-guided optimization, where during search, the core-guided solver will introduce new variables and reformulate the objective on the fly to help with solving. So in our approach, rather than going by trial and error, we use a core-guided solver to identify some possible cores, which represent new variables we could add. We try to figure out where in the model these came from and associate them to some instance data. Then we try to generalize these across several instances. And then we start to modify our model to introduce the new variables and reformulate our objective. In practice, the reformulations that we find have been quite good at improving the performance of lazy clause generation solvers, and in some cases we can also improve the performance of pure CP solvers. The main contributions of the paper are that we show that it's possible to lift cores from a set of instances to the model itself. Improvements can be found by just grouping sorted terms based on relatedness, and we show that our methodology can help a modeler discover usefully related terms. Welcome to this presentation on our paper on core-guided model reformulation. In this paper, we wanted to address one of the main limitations of constraint programming-based optimization, in particular that CP models tend to have additive objective functions, and CP solvers often underperform on these. This is because it's often difficult for a CP solver to improve the lower bound on these kinds of functions. As an example, we have this constraint program here, where a CP solver will not be able to find a better bound for our objective variable z, because any one of these objective terms could comfortably be set to its lower bound without affecting the satisfiability of the constraint. One way we could help our CP solver in this case is by introducing new variables and reformulating the objective. As we can see here, we've introduced a big X that combines the x's from the objective function and provides a good bound on this subset of the objective. And in this case, the CP solver is now able to find a good lower bound on our objective variable. There are, of course, many different reformulations that we could try. For example, if instead we combined the x's and the y's under individual new variables, we would not have found the same lower bound. Core-guided solvers do this kind of model reformulation during solving for individual instances. So how do core-guided optimization solvers work? Well, they work by first setting the objective terms to their lower bounds and searching for a solution. If there's a failure, they return an explanation in the form of a core. They introduce a new variable, in this case we call it P1, which combines the variables from the core and infers a good bound for that introduced variable. It then replaces the terms that it groups in the objective function, and we get a better bound for the entire objective function. This process continues, again fixing all of the variables, all of the objective terms to their lower bounds, and it introduces more new variables and does more reformulation until we're just working on these new variables, and we increase the bounds on these until we find a satisfiable solution. And because we've been pushing the lower bound, once we find a solution, it's an optimal solution to this problem. So in this paper, we want to find useful reformulations of objective functions for a model, not just instances. Where we're going to use core-guided solvers to find cores for instances, and we're going to try to look for cores that are useful across instances by looking for patterns, and we want to try to determine why are they useful. Once we find these, we'll try to group these objective terms in such a way that useful combinations appear together, and then we will take these orderings and perform this kind of recursive decomposition to construct our reformulation. Note that because we're working at the level of a high-level constraint model, when we introduce our reformulations, they're not tied to a specific instance, but when it's actually compiled for a particular instance, it'll be tailored for that instance. So in this presentation, we're going to use the RCPSP wet model as our running example. The RCPSP wet problem is a resource-constrained project scheduling problem where we have, as parameters, we have durations for each task. We have resource requirements per task per resource. We have a chain of successors representing the precedences between tasks. We have resource capacities, and most interestingly, we have these deadline variables, which represent an ideal start time and a penalty for starting early and a penalty for finishing late. The task is just to find an assignment to the start times for the tasks that minimizes for each task the sum of the earliness penalty and the tardiness penalty for that task. So the methodology that we use to find a reformulation for this problem is to first find a set of core candidates, then searching within those candidates, we want to find interesting ones. And then once we have those, we want to perform a reformulation of the objective function. So first, we need to find our cores. In our case, we use a core-guided lazy clause generation solver called Geese. In terms of instrumentation, it already has a verbose mode that outputs cores. But unfortunately, it outputs cores in this format where it talks about variables that don't appear in the model and are hard to interpret. As such, our first task is to rename these variables and tie them back to expressions in the model. Once we do this, we're able to see that this core talks about the earliness of task 16 and the tardiness of task 25. Following this, we generate cores for several instances of the problem, and we throw away cores that contain more than one literal. We then also rank the cores based on how much of an improvement they've had to the lower bound on the objective. Now that we have a bunch of cores, we want to select the good ones. So the way that we approach this is that we look for patterns in the cores. And we'll find things like this, where we'll find cores that are of this shape in several instances of the problem. In particular, we see that there are lots of cores that talk about the tardiness of one task and the earliness of a different task. So once we had identified this, we want to figure out what the reasons were that these earliness and tardinesses of two different tasks were showing up together. And this step usually requires in-depth knowledge of the problem. What we had to do was we generated Gantt charts of the instance data, and we realized that in many cases, tasks A and B were often direct successors that overlapped in time. And what the core was saying was that because these two tasks overlap, at least one of them will have to incur a penalty. And when we found this, we later used this to construct a reformulation. So now we have our patterns and we have some reasons for why they're present. And we try to reformulate the objective function. So with simple reformulations, we can just define an ordering that puts useful core terms near each other. And then we recursively build this, this objective function. So we've implemented this group function in Minisync, and it's quite easy to use, pretty much as just a drop-in for the sum constraint. For the RCPSP wet model, we have two main reformulations. The first was just a naive experiment that simply ordered the tasks in the order of their start times and applied this group function. The other reformulation tried to emulate the cores that we saw by finding tasks that were direct successors and had an overlap, and we just automatically added in that new variable. For CP solvers, it is often not sufficient to just add these new variables. You also need to have good bounds. So for example, when we're adding these new variables in the direct reformulation, we also need to add a lower bound that represents the minimum cost for moving task I earlier or task J later. In terms of automation, we've automated the first step pretty much completely. So the solver has been instrumented, we can collect our cores, and we can do the renaming automatically. However, we would like to do a bit more. In particular, we can see a way to do the pattern generation based on the techniques from Zagami et al. But other steps require a bit more expert knowledge and are hard to automate. However, we can provide some tools that help, even if we don't have full automation. An example of this support can be found in the FindMust tool. This tool can be used to identify minimal unsatisfiable subsets in constraint models, and it ships with the Minisync bundle. The way that we used it in our CPSP wet was we added name constraints or name annotations to expressions in a model. We added our core in a negated form to our model to create an unsatisfiable model, or this was for a specific instance. And we ran FindMust. And something that was quite powerful about this is that it can give us the chains of tasks that are responsible for this core. So tasks 27 and 17 are not immediate successors, but they are ancestors through task 24. And using this, we're able to get greater insight into what these cores mean. It can also give us explanations for cores that are a lot harder for a user to find on their own. So this kind of explanation would take a long time for a user to infer on their own. So to evaluate our method, we looked at the top 5 mini-zinc challenge models where the core-based optimization with geese performed drastically better than branch and bound. This gave us these 5 benchmark models, and for each one we applied our method using just 2 instances from the problem, typically a small instance because it's easy to interpret the cores, and a slightly larger instance so that we can test whether our reformulation scales or whether there's some other structures in larger instances that we haven't anticipated. Each instance and reformulation was executed with G-code, which is a straight CP solver, Chuffed, which is an LCG solver, and Geese, which is an LCG solver, and we disabled core guided search. For each model, we always have the original objective function. We also have a naive reformulation where we simply replace the objective function with a call to group, which does the recursive decomposition. We also tried having a random decomposition, which simply shuffles the terms that would normally go to the group function. However, this is often not very good, so we've left it out. Here are the results for our CPSP wet. So for each instance, we see the results for G-code, Chuffed, and Geese. And we can see, so each bar represents a different decomposition that are listed here. We can see that for Geese and for Chuffed, our reformulations tended to improve the performance drastically. Note that this is on a log scale. But for G-code, we often didn't improve performance too much. However, with the direct bound reformulation, which is the direct reformulation with extra bounding, or with those extra bounds, in some cases, G-code is able to find a solution, or find the optimal solution and finish before the timeout. And in other cases, it's able to find a better objective value. So I'll move quickly through the other models. So for C-moving, we had 2 different reformulations, and again, they performed well for lazy clause generation solvers, but not for a CP solver. For JP encoding, again, we had these 2 reformulations that performed well for LCG and not so well for CP. For rel2 onto, so this was interesting that we found a reformulation that performed well on our small instance. When we moved to a different instance, we realized that there were structures in the data that we needed to address. So we came up with this merging strategy. And for the Spot 5 model, we also had some reformulations, and these performed well for lazy clause generation solvers again. So in conclusion, we show that it's possible to lift cores from sets of instances to a model itself. The improvements can be found by just grouping the sorted terms based on relatedness. And the method supports a modeler's discovery of usefully related terms. In practice, it performs, the reformulations perform really well on LCG solvers, and having good bounds for CP solvers is really important. In future, we aim to automate the system a little bit more. In particular, we want to automate the pattern generation, and we want to integrate the Moss enumeration a bit more.